Hey guys, so we're in chapter 3 now. You've already finished your test. Now you're watching these notes. All right. So I'm going to be using 3 different color highlighters today. I'm using orange, yellow, and pink. I am going to be color coding some things, so that's why I figured I would let you guys know ahead of time. So if you want to get those ready, you can pause and get them ready. And here we go. So we're going to continue on with this. You can use a secant line to approximate the slope of the tangent line. We get a better approximation the closer the 2 points the secant passes through are to the point we're trying to find for the tangent line. So the closer that secant is to the point of tangency, the better approximation we're going to get. Okay, so let's look at example 1. I know it looks hard because it's a word problem, but it really isn't that bad, I promise. Okay. So we have that a zoo sponsored a one-day contest to name a new baby elephant. Zoo visitors deposited entries into a special box between noon, t equals 0, and 8 p.m., t equals 8. The number of entries in the box, t hours after noon, is modeled by a differentiable function, e, for 0 less than or equal to t less than or equal to 8. Values of E of t in hundreds of entries at various times t are shown in the table above. Use the data in the table to approximate the rate in hundreds of entries per hour at which entries are being deposited at time t equals 6. Show the computations that lead to your answer. Okay, so we're going to approximate the rate. Okay. So we're approximating, and when we are finding a derivative, pretty much that's what it is, we are finding the slope. So since we're approximating and we're using the secant line to approximate, we're going to use the slope formula. So y2 minus y1 over x2 minus x1. Okay. All right. And they want us to find at a specific time. At a time t equals 6. Well, let's look at our table. We have 0, 2, 5, 7, and 8. 6 isn't on there. 6 obviously is going to be between 5 and 7. So that's where t equals 6 is going to be. So that means I'm going to need to use these 2 points that are the closest to it to approximate the slope, the derivative. Okay, so y2 minus y1, 21 minus 13, over x2 minus x1, so 7 minus 5. 21 minus 13 is 8. 7 minus 5 is 2. 8 divided by 2 is 4. So remember, we had to approximate the rate in hundreds of entries per hour. So if this is 4, that means that there were 400 entries per hour. And that's the answer. Oops, guys can't see. Okay. Example 2 is very similar, but because I don't want this lesson to be so long, we're going to skip it. All right, so let's turn the page. Example 3. We're going to use secant lines through the given point to estimate the slope of the tangent lines at the midpoint, and then we're going to sketch a graph of the estimate of the derivative. Okay, so we're going to start with what are we trying to do here? Well, we're going to be estimating the slope of the tangent lines at the midpoint, and then sketch a graph of an estimate. So sketch graph of an estimate of the derivative. Okay, so we have y equals x squared. That is our original function. So to find the y values, all we have to do is plug in these x values. So let's go ahead and do that. So when we plug in a -3 squared is 9, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1, 4, 9, because it's a parabola, it's parent function. Okay. And what we need to do is we need to find the midpoints and the slopes to estimate the derivatives graph. So we're going to need the midpoints between our points, and we're going to need the slopes. Because remember, when we take a derivative at a specific point, that derivative ends up being our y value, because it ends up, it's the slope of the tangent line at that point, at that particular point. Okay, so hang in there with me if you're like, oh, I'm a little bit confused. It's okay. You'll get it once you see what we're doing with it. So let's first look at the midpoint between the first 2 points, the midpoint between -3 and -2. Well, halfway between -3 and -2 is -2.5, -2.5. Okay. All right, let's find the slope. So we need to get the slope, which means we're going to need to use the slope formula, y2 minus y1 over x2 minus x1. Never thought you'd be using that so much, huh? Okay. And now let's find the slope between these 2 points using that formula. So remember, the slopes are the same as finding the derivative, okay? And we'll have, let's see, y2 minus y1, because this one's further away from 0, so I'll count this, y2, y1. So I'll have 9 minus 4 over -3 minus -2. I have a double negative, turns to a positive down there in the denominator. 9 minus 4 is 5. -3 plus 2 is -1. So my slope, my derivative, is approximately -5. Because technically this is average rate of change, and we know that the derivative is instantaneous rate of change, but we're approximating, so it's about -5. It's an approximation. Okay, next one. So let's go to the next 2 points, -2 and -1. We'll find the midpoint between those two. Excuse me. The midpoint between -2 and -1 is -1.5. And now we need to find the slope. So for this part, I'm not going to write it down. We're just going to do it in our heads. So we'll have in the numerator y2 minus y1, so 4 minus 1, which is 3, so keep the 3 in your head, over -2 minus -1. So that's going to turn into -2 plus 1, which is -1. So I have 3 over -1, which is -3. If you need to write it down, write it down. I'm just not going to. All right, next one. So now I need the midpoint between -1 and 0. Well, halfway between 0 and -1 is -0.5. Okay. And using the slope formula on those 2 points, it would be 1 minus 0, which is 1. Keep that in your head. And then over -1 minus 0. So 1 over -1 is -1. Okay. Next one. The midpoint between 0 and 1 is a positive 0.5. And using the slope formula, 0 minus 1 is -1 over 0 minus 1 is -1. -1 over -1 is positive 1. Okay. And then between 1 and 2, the midpoint between 1 and 2 is 1.5. Okay. And then using the slope formula, 1 minus 4 is -3. Over 1 minus 2 is -1. -3 over -1 is positive 3. Okay. And then, guess I'll use red again. Between 2 and 3, the midpoint between 2 and 3 is 2.5. And using the slope formula, 4 minus 9 is -5. Over 2 minus 3 is -1. -5 over -1 is positive 5. Okay, so let's go ahead and graph these. I don't even know why I said scratch. I don't even know. I got distracted. I heard my son screaming in the background, and it just seems to be the norm these days. But anyways, let's plot this. This is going to be, it's x squared, so we know it's a quadratic. We know it's going to be a parabola on this graph, okay? So we have a point at negative 1, 2, 3, 9, 1, 2, 3, 4, 5, 6, 7. It only goes up as high as 7, so I can't graph that one. That's okay. Negative 2, 4. Negative 1, 1. 0, 0. 1, 1. 2, 4. 3 9s off my graph. There's my pretty parabola. Okay. And this is the original graph. All right, let's look at what the next one is going to be, what the derivative graph is going to look like. And this is the derivative of the whole thing, of what it looks like from the derivative of the slope of this tangent line to the slope of this tangent line to the slope of this tangent line to this tangent line to that tangent line. What does it look like all together as just a derivative graph is what we're trying to find out. Okay, so we're going to have the point. So these are all 0.5s. Okay, so I'm just going to mark all the halfway marks on here, halfway between each whole number, just to help me out, help guide me when I'm graphing it. Okay, so I have negative 2.5, negative 5. So negative 1, negative 2.5, and then down to negative 5. 1, 2, 3, 4, 5. So right here. And then negative 1.5. So negative 1.5, and then 3. 1, 2, 3. I don't know why I'm so shaky. And then negative half, and then negative 1. And then 0.5, positive 1. And then 1.5, 1, 2, 3. And then 2.5, 1, 2, 3, 4, 5. And because I have those dots so nicely lined up and I don't want to screw it up, I'm going to use my little protractor here to draw a straight line. Okay, and we see based on our graph that this is linear, isn't it? So the original function was a quadratic and its derivative function is linear. Okay, so let's analyze this a little bit. So this is where I'm going to start color coding some things. I'm going to start off with yellow. If we look at this side of the parabola, this is all decreasing, 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 decreasing. So any tangent line along that side of the parabola is going to be a decreasing line. It's going to have a negative slope. So let's write that. This will have a negative slope. So if it has a negative slope, that means that the derivative is negative. So if the derivative is negative on the derivative function, that means that's the part of the graph over here, because that is below the x-axis. That's where those y values, those slopes, are negative. So since this whole part is underneath the x-axis, this represents that left side of the parabola, of the original function. Okay. Then we get to right here, where we're on the x-axis. Because we're on the x-axis, that means if we draw a tangent line, it's a horizontal line. And the slope of a horizontal line, well, the slope is 0, so the derivative of 0 would be 0. So that's this point right here. We call that a turning point. When it crosses the x-axis like that, that means we're going to have a turning point. So that turning point is represented by the point there at the origin, where it switches from negative to positive. We also call that an inflection point, where it just starts turns around. Okay, and then we have the right side of the graph, where it is increasing, 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 increasing. So if I were to have a tangent line along that side of the graph, no matter where I go, this line is going to be increasing. It'll never be decreasing. So it'll be above the x-axis. Its derivative will be a positive slope, and it will be above the x-axis. So that represents this portion of the graph. So this is where we are above the x-axis. So now we're kind of piecing together everything we've learned so far, and we're trying to analyze, okay, well, what does this mean to the graph? And what does this mean to the graph? Okay. So let's also not forget that the new graph, this is representing the derivatives, which means it's representing all the slopes of each of the tangent lines along that parabola. Okay, so let's keep that in mind. It was all about the slopes. All right, so let's try another one. Y equals x cubed. Normally in class, I would have you guys try this one on your own. But so if you press pause and try it on your own, on your honor, try it on your own and see how you do. And then if you get stuck, you can press play and start again. Oh my gosh, I have ink like all over me. What did I do? Oh my gosh. Okay. Anyways. All right. So hopefully you press pause and you try that out on your own. All right. So plugging this in, -3 cubed, -3 times -3 times -3 is -27. -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is +27. Okay. So when I go to graph this, might as well graph it since I'm there. -3, -27 is way the heck down here. It's not on my graph. So I'm not going to worry about it. -2, -8. This only goes down to -7, so I'm not going to worry about that. -1, -1 is there. 0, 0, and 1, 1. And we know that this is not a diagonal line. We know this is a cubic, so it looks like this. We learned this last year in Math 3, right? Cubics. Okay, so this is our original graph. Okay, this is the OG, the original. Okay, and it's y equals x cubed. It's a cubic. Okay, so I wonder what our derivative function is going to look like. Okay, so remember that the x values have to do with the midpoints, finding all the midpoints in between points from our original graph. And the y's are the slopes, the derivatives, the y primes. Okay, so let's first look at the midpoint between -3 and -2, we know is -2.5. And then notice these are all the same numbers as the problem up above, so we know what these midpoints are going to be. -1.5, -0.5, 0.5, 1.5, and 2.5. So no need to go through all that again if we know what it's going to be. And then let's find the slopes. Okay, so -27 minus a -8 is going to be a positive 9, or it's going to be a -19. Sorry, over. If we subtract these, it'll be a -1. -19 divided by -1 is +19. Okay, so I'm just going to go ahead and tell you what the slopes are going to be, because I don't want to go through all that again. We know how to use the slope formula. So it's going to be 19, 7, 1, 1, 7, 19. Okay. And let's go ahead and graph what we've got. So I like marking my halfway marks just to kind of help guide me when I'm doing these. So -2.5, and then 19 is off my graph. That's okay. -1.5 and 7, 1, 2, 3, 4, 5, 6, 7, right at the top. Just enough. And then -0.5 and then 1, +0.5 and then 1, 1.5 and then 7, and then the other one's off my graph. So it almost looks like I'm missing a vertex, like it's going to be a parabola. Well, if I think about it, if I look at this function, there's technically what we can call like a shelf right here at this point 0, 0. So at this little shelf here, if I were to have a tangent line just at that point, it would be 0 because the slope would be 0 because it's a horizontal line. So if the slope is 0, that means the derivative is 0. So we would have a point right there. So it really does make a parabola. Okay, so we had a previous example. The first example, the original function was x squared, and its derivative ends up being linear. This time the original is an x cubed, and the derivative function ends up being a parabola, an x squared. So what do we notice? I'm also going to highlight that. I want that to stick out for you guys. What do we notice? And normally I would like have you guys discuss it a little bit. We'd have some back and forth on what we're noticing here. But what you should be noticing is that the derivative function drops down 1 degree. A degree less than x squared is just an x, which is just a line. A degree less than an x cubed is an x squared. So let's answer our question in our notes so that we have it there. We can say the derivative drops 1 degree. Okay, once we start seeing a pattern, we can assume that that pattern is going to continue. Okay, so that kind of helps us when we're trying to figure out what the derivative function is going to look like. Okay, so let's analyze this a little bit. So if I were to draw a tangent line along the original here, I would have a positive slope, positive slope, positive slope, no matter where I went. So that means that all the slopes would be positive, which means all the derivatives would be positive, because the slopes would be positive, which means that everything would be all above the x-axis. If the derivatives are all positive, then they're all going to be above the x-axis. And isn't that what we see there? It is. So the patterns check out. They check out so good. It's a lot of analyzing in calculus. So we're trying to understand, okay, what's going on? What does this mean? And it's all just taking the math that you guys have learned over the years and just kind of picking it apart and trying to understand, well, what is this telling us? Okay. All right, I'm going to be color coding some things with my highlighters. It says, notice that when the slopes of the original graph are negative, when the slopes of the original are negative, the graph is decreasing. The graph of the derivative is below the x-axis. So when the original graph is negative, where the graph is decreasing, the derivative will be below the x-axis. Okay. Also, when the slope of the original graph is 0, so slope of the original graph is 0, the graph of the derivative passes through the x-axis. So when the slope is 0, the derivative is going to pass through the x-axis somewhere. Kind of like at that inflection point. And when the original function is increasing, the graph of the derivative is above the x-axis. So when the slope is increasing, we're above the x-axis. When it's decreasing, it's below the x-axis. And when it is 0, it is passing through the x-axis. Okay, so we have example 2, given the original graph, sketch the derivative. So we're just sketching it, okay? So let's analyze what's happening on this original graph. This is the original graph. So I'm going to start from left to right. So I see this part right here. It's increasing, increasing, increasing from -3 to -1, okay? I can also tell that its slope, up 1 over 1, so it's constant, has a constant slope going up 1 over 1 each time. We're also going to write it's constant. Okay. Then the next portion of it, flat lines from -1 to 0, or flatlining. So that means the slope of a horizontal line would be 0. Okay. That's also constant. Then we are increasing, increasing, increasing. And it's constantly increasing because we're going up 1 over 1. So again, it's increasing at a constant rate of +1. And then that last part of the graph, we're decreasing, decreasing, decreasing. And it is constant, and we're decreasing by down 1 over 1. So it's a constant decrease of -1. So we have a positive slope, a zero slope, a positive slope, a negative slope. Okay, now we have enough information to graph what the derivative would look like. It isn't always what you're going to think, because this one's a funky one. So we can't just say, oh, it's going to drop a degree like it did in the last couple examples, because this is a piecewise function. Okay, so I need 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3. Let's label our graph. Okay, so I'm going to continue on with my color coding. So between -3 and -1, it's increasing by a slope of 1. So at -3, the slope is 1. At -2, the slope is 1. At -1, the slope is 1. You guys with me? Over here, at -1, the slope is 0. Then at 0, the slope is 0. Okay, still with me? Oh, I'm on green. Then for this portion, at an x value of 0, the slope is a 1. At 1, the slope is 1. And at 2, the slope is 1. It's constant, so that's why it's a flat line, constant slope. And then for that last portion, it's a decreasing slope by 1. So at 2, the slope is a -1. At 3, the slope is a -1. And there we go. Here is our y prime, our derivative function. Isn't that easy? Isn't that kind of scary how easy that is? Doesn't that freak us out? We're going to skip this one. Example 3 says, given the graph of the derivative, sketch the graph of the original function. Okay, so we have the graph of the derivative this time, and we have to sketch the graph of the original. That means we are going backwards. So we're doing the reverse of what we just did in the last example. Okay. And just to help soothe your fears, it's not going to be exact. We're sketching. It's an estimate. Okay, so don't freak out about that. We're going to be guessing at the y values of the original function. There's no way we're going to know exactly what they were. We're just guessing. So sometimes my graph might be different from yours when it comes to these types. Okay, as long as it has the same key characteristics, that's all that really matters. Okay, so we're given the graph of the derivative. So that means we're given the graph of all the slopes. Okay, so let's analyze what we have here. So we have this first little bar. So the slope is constant, 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 constant at a y value of -1. So we have a constant slope of -1. Okay. Then we have this middle portion of the graph that doesn't look like it's even touched. We have no idea what's going on there in the middle. We don't know what's going on there, but that's okay. We can still do this. Then we get to up here, and it's constant, 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 constant. The y value is at a +2, so we are at a constant slope of 2, +2. Okay, so when the slope is positive, remember, that means this is where the graph is increasing. And on the flip side, When the slope is negative, this means that that's where the graph is decreasing. Because the tangent line slope is negative, means it's a decreasing line. Okay, so we're going to give our best little guess here of the sketch of the original function. Just setting it up. I might need to make this a little bit bigger. Okay. All right, just setting it up. All right, so for the first part of the graph, we know that we are decreasing from -6 to -2. Okay, but we're constantly decreasing. So constant means linear. Okay, so from -6, I'll just start up here. We're constantly decreasing until we get to -2. So let's see, I'll start up here. We're decreasing by a slope of 1 each time. I'll just stop when I get to -2. And notice how there was a closed point there, so I can have a closed point here. So we're decreasing, decreasing, decreasing. Okay. Then, we don't know what's happening in the middle, but we do know from -2, it's increasing by a slope of 2 from there, and it's an open point. So there's an open point around there from where this part of the function continues, and it has a slope of 2. So up 1, 2 over 1, up 1, 2 over 1, up 1, 2 over 1. Okay, so I do want to point out right here, since this is our little switch point there, it's not a turn, okay, because we didn't have a, we don't know, okay, so we don't know exactly what happens other than it's not a max or min point. Or, sorry, max or min, probably should put turn. Like a U-shaped graph. It would be if we had a slope of 0 in here, but we don't have anything that shows that. So we don't know. Okay, so we don't know exactly what's happening there at that turning point. We do know it's not a U. It's not an actual like turn. Okay, it's a sharp turn, not a curved turn. All right, let's take a look at letter B and do the same thing. So we have the derivative function, and so that means that we have the slopes. Because we have to put our brains in that mindset. Okay, I'm looking at the slopes. I'm not looking at anything linear piecewise. I'm looking at the derivatives. I'm looking at the slopes of a function. What was that function, pretty much? Okay, so I'm noticing that we are in the negative. We're below the x-axis here. So that means that this part of the graph is where the slope is decreasing. And since it's not a flat line like it was up here, that means that the slope is not constant. It's not staying the same number. At -4, the slope is -3. At -3, the slope is -2. At -2, the slope is -1. At -1, the slope is 0. Okay, so this is telling me that these are all negatives. Okay, it's where it's decreasing. It also means the slope is decreasing. And since it's not the same number each time, let's put in parentheses, it's not constant. We don't have a constant slope going on here because there's no flat line going on for the derivative. Okay. We also know that we are crossing the x-axis. So whenever we cross the x-axis like that, that means we're going to turn. We're going to have a turning point. So there is going to be a curve in our graph. Is it a max or a min is what we're going to need to figure out. Okay. And then the derivatives are above the x-axis, so they're positive, which means that we are increasing on the original graph. Okay, so if we're increasing and we're above the x-axis, it just means that since it's not a flat line, it's just getting steeper and steeper and steeper each time. Because at -1, the slope is 0. At 0, the slope is 1. At 1, the slope is 2. So the slope is increasing steeper and steeper each time. Okay, so let's put in our little notes. Slope is increasing. And it's getting steeper. Okay. And then we have this little piece down below from 1 to 3. It's below the x-axis, so that means that the slope is decreasing. And it's not a flat line, so that means that the slope is decreasing and getting steeper and steeper and steeper. Slope is decreasing, steeper. You're probably thinking, okay, we've analyzed it, Miss Garcia. I'm probably a little bit confused on what I'm supposed to be sketching now. Don't be. Don't overthink it. It's not going to be as bad as you think. Sorry about that, guys. I had to pause for a second because my husband turned on a really, really loud fan. Okay. He just can't wait until I'm done. Okay, so remember, this is supposed to be a sketch of what the original graph could look like. Okay, it's not going to be exact. It's just it's an estimate. It's a sketch. Okay, so we know a couple of things. We know from -4 to -1, the slope is decreasing. So here's -1 on our graph, and we can just fake it, really. So boom, 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 boom. It's decreasing until we reach -1. Okay. Then at -1, that's our turning point. So it's going to turn from here, and we're going to increase all the way up to an x value of +1. So here's +1. So we're going to increase, 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 increase until we reach +1. Okay. And then the slope is decreasing, and it's getting steeper and steeper and steeper each time. So boom. So there's a quick sketch of what that original graph looked like or could look like. Okay? Answers can vary on that as long as you're following where the turns are, where it's increasing, where it's decreasing, that type of thing. Okay? Turn the page. All right. An alternate derivative definition. How about that? So there are different ways to find the derivative. And so here's an alternate. So we have learned the definition of the derivative, but it turns out that there are many ways to describe the same concept. So this is an alternate derivative at a point, just like what we have done with the limit as h approaches 0 of f of x plus h minus f of x all over h. Same type of thing. It does the same stuff. So we're still talking about instantaneous slope, the slope at that instant. So it's still instantaneous rate of change, another word for slope. So it's still the same thing, because why would we say the same name and mean something different? No, it's the same name, so it means exactly the same thing. So it's the derivative of the function f at the point x equals a, so f prime of a is the limit as x approaches a of f of x minus f of a all over x minus a. So this is the different part. We're used to f of x plus h minus f of x all over h. So this is going to be a little bit different, but it's actually a little bit easier. So each time you learn a new way to take a derivative, it's going to be a little bit easier all the time. Okay, so we're going to start with example 4. Differentiate the following using the alternate definition. So I'm going to start with example B. So we're going to skip A. If any of you want to see example A, just ask me and we can go over that in like tutorial or something. So letter B, y equals 3x squared plus 2x at x equals negative 1. And we're going to follow that new definition, an alternate way to find a derivative. So we're going to be using the new way. Because now this is the way. Did you guys catch my Mandalorian reference in there? Mandalorian season 2, August 30th, or not August, October 30th. Oh, so excited. Can't wait. I love Mandalorian. All right, so let's set this up. So it's the limit as x approaches a. So this is our a value, a negative 1. So we're going to have the limit as x approaches negative 1 of, we need f of x, so the original function, 3x squared plus 2x minus, now f of a. So that means we have to plug in the negative 1 into that function. So minus, and I'm putting it in parentheses because it's a group of terms. So plug in the negative 1 for x on the x squared, plug in the negative 1 for x with the 2x, and it's all over x minus the a value is a negative 1. Okay. All right, so negative turns to positive because it's double negative. I know that 2 times negative 1 is a negative 2. Negative 1 squared is positive 1, so 3 times 1 is 3. Okay, so let's rewrite this. We'll have the limit as x approaches negative 1 of 3x squared plus 2x minus 3 minus 2 is 1, so I'm going to have minus 1 all over x plus 1. Well, that's simplified to something a little bit nicer, huh? We know how to do that. We learned that in the last chapter. We just took a test on it. So we better know how to do it, right? So we need to factor this. So we're going to have the limit as x approaches negative 1 of something all over x plus 1. You use product sum on this. The product is negative 3. It's got to add up to 2. Okay, so I'm going to use guess and check. So we know that we're going to need to get a 3x squared. So 3x times x will give us that 3x squared. Okay, we're going to need to get a negative 1 product. Okay, so that means that one of these must be negative and one of these must be positive to get that negative 1 product. So let's check it out. 3x times x is 3x squared. 3x times 1 is 3x. Negative 1 times x is negative 1x. And then remember, 3x minus 1x is a 2x. And the negative 1 times 1 is negative 1. So it checks out. Okay. So you don't always have to do product sum out the whole way. Sometimes you can guess and check. Sometimes my brain, I can't, for the life of me, guess and check well. Like I remember I tried to do it in front of you guys in a Zoom and I got stuck and then I had a brain block and then I'm like, you know what, I should have just done it the long way to begin with. So, and sometimes that happens. So yeah, at least that's what happens to me. All right, these cancel out because that's a whole. It's a whole. Okay. And now, since the denominator was the problem, I couldn't plug in a negative 1 into the denominator. It made it 0. Now I could plug in that a value of negative 1 in for x. So I'm going to have 3 times negative 1 minus 1. So that's going to be negative 3 minus 1, which equals negative 4. So the derivative is a negative 4. How about that? We just used this alternate method. We didn't do the whole x plus h minus f of x all over h type thing. We didn't do that. So this way is actually a little bit shorter. And each time you learn a new method, it will be a little bit shorter. But I can't just show you the shortcut right away because we need to understand where it comes from. And that's a huge deal with calculus, okay? Got to start with the basics. All right, so that page is done. Next page, we have notations for derivatives. Okay, so we've seen the prime, y prime. It's nice and brief, but it does not name the independent variable. Doesn't tell us what the independent variable is going to be. You're going to see dy over dx. When we say it out loud, we say dy dx, or the derivative of y with respect to x. And it names both the variables and uses d for derivative. D stands for derivative. How about that? That's pretty easy, right? df dx, this is when we're in function notation. So df dx, or the derivative of f with respect to x, so f of x, it emphasizes the function's name being f of x. And then d dx of f of x, so d dx of f at x, or the derivative of f at x. It emphasizes the idea that differentiation is an operation performed on f. So all of these notations mean exactly the same thing. It's notation for the derivative. So you're going to see them all. They all mean the same thing. Why all the notation? The prime notations, y prime and f prime, come from notations that Newton used for derivatives. You know, the laws of Newton, you know, the apple falling from the tree, gravity, that type of thing. You remember. Sir Isaac Newton. The ddx notations are similar to those used by Leibniz. Each has its advantages and disadvantages. Leibniz is another famous mathematician, physicist, okay? All right, so example 5, write the derivatives of the following functions 3 different ways. So we're given function notation here. It's g of x, so that's the name of the function. So we can use, that's y's and x's, so we got to use one of these. So we can say, well, since it's not f, it's g of x, we can say dg dx. Or we could use this one. We can say it's d dx at g of x. Or we can use what we've been using. We've been using the primes, g prime of x. So those are 3 ways for that one. And then the same thing would go with the m of t, except you're using m's and t's instead of g's and x's. All right, so your homework is in the book, page 105, these problem numbers, and make sure you show all your work. Upload a clear picture into Google Classroom for me. Please make sure the pictures are upright. When they're sideways, that makes me very sad, and I'm going to have to start telling you guys to resubmit them. So please don't make me do that. All right, guys, have a great day.